In this video, we're going to learn how temperature can be used to affect the phase stability of pure substances. This video is a follow-up on a video in which we have seen how you can modify the stable phase of a substance with pressure. Alright, so what we have done in that prior video is recall how the molar Gibbs energy, which is the thermodynamic variable that determines phase stability, depends on the conditions, pressure and temperature. Right, so for pressure it depends as the molar volume. For temperature, which is what we're concerned with in this video, it depends as the minus molar entropy. Right, so what we're going to do is try to add some thermodynamic foundation to some facts that we know from experiment, right? And the facts are that if you have liquid water ambient conditions and you cool down at constant pressure, then you will eventually get ice, right? So the stability of the phase changes from liquid to solid. However, if you have the liquid water and you increase the temperature, then you will vaporize that into a gas, right? So somehow the molar Gibbs energy of the gas becomes lower than that of the liquid and the solid if the temperature is high enough. Right, so the question is, how does thermodynamics bear out that knowledge that we have from time immemorial? Okay, great. So the way that we're going to proceed is exactly the same way as what we've done with pressure, and that is to simply represent the variation of the molar Gibbs energy, but with temperature at constant pressure. So let me draw that for you. And again, this is something that we have done in a prior video. What we're doing now that is new is examining phase stability from this diagram. Alright, so this is temperature, that is molar Gibbs energy, and this is at constant pressure, which I'm going to write right here. This can be anything. Generally, we're going to be interested in 1 bar pressure, atmospheric pressure, or near ambient pressure. And then once you have the pressure constant, you can then just draw how the molar Gibbs energy depends on temperature. And the way that it depends is as the minus molar entropy. Now we know that the molar entropies of phases are different. We always know that gases are far more entropic than liquids than solid. That means that they have a larger molar entropy. Molar entropies are always positive. That means that all of the lines that you're going to see in this graph will have negative slope, because the dependence of the molar Gibbs energy with temperature is as the minus molar entropy. Alright, so let's get started with that. I'm going to draw then the lines for the gas, liquid and solid. So the line of the gas is going to have negative slope, and because the molar entropy of the gas is the largest of the 3 phases, then it's going to have the largest slope. Right? So let me draw that as something with a pretty sizable negative slope, and this is the line of the gas. Well, very good then. How is that going to work for the liquid then? Well, for the liquid, which I'm going to use a blue trace for, is going to be a line that is also of negative slope, but it's going to have much less negative slope than that of the gas. So let me draw that as perhaps something like this. Okay, that is the liquid line. And for the solid, you're going to have a line with even a smaller slope than this one. Alright, so let me see if I can draw that as perhaps this. Alright, so still negative slope, but notice that that is smaller than the one in the solid. Okay, very good then. Now the question is, what can we learn from this graph? Can we learn something about the stability of the phases? The answer is yes. Remember that the phase of lowest molar Gibbs energy at any condition of pressure and temperature determines the phase that is stable. Okay, so when we come here, suppose that this is now liquid water, or actually water in general. You take that water sample and elevate the temperature to really high temperatures at constant pressure, and what you see is that the line of lowest molar Gibbs energy, right, is the gas. This line is below that of the liquid and the solid, and that means that at high temperature the gas is the stable phase for actually all substances, and that is really, really good. It's something that we knew from experimentation, but now we know how thermodynamics allows you to understand that, right? It's just the fact that the molar Gibbs energy of the gas is below that of the liquid and the solid at high temperatures, and you see that up here. Now, if we cool down, right, so suppose that we have this temperature initially, and now we cool down. This still means that the gas is a stable phase until you get to that crossing point. At that point, you have that the Moore Gibbs energy of the liquid and the gas is exactly the same, right? So I'm actually going to draw here an arrow and write exactly what the thermodynamics there is. Notice that at that point, what you have is that the Moore Gibbs energy of the liquid phase is identical to the Moore Gibbs energy of the gas phase. Alright, so you can set up a phase transition liquid to gas, and what you will find is that delta G is 0. And that is a hallmark for an equilibrium phase transition. Okay, so that is the equilibrium vaporization or boiling point of this particular substance, okay, at this temperature. So we can label that as T sub B, boiling point. Okay, great. Well, if you, at constant temperature, cool down from the boiling point, what you see is that now is the line of the liquid that has the lowest Moore Gibbs energy, right? The blue line is below that of the solid and that of the liquid. So liquid is a stable phase. And you continue to cool that down until you get to a crossing with this line of the solid. And at that particular point, what happens is that the Moore Gibbs energy of the solid is identical to the Moore Gibbs energy of the liquid. Right? So that also implies that you have thermodynamic equilibrium between the two phases. That is the equilibrium melting point or freezing point. Okay? And if you cool down past that freezing point, what you have is that the solid is the stable phase. Right, so let me actually label this as freezing or fusion point if you want to, and this is just temperature in general. All right, so notice how beautiful this is. We're learning how to connect experimental observables like freezing points and boiling points with thermodynamic values, which are the Moore Gibbs energy. What we have seen in this video is a way that you can use thermodynamics to understand why gases are the stable phase at really high temperatures and why solids are the stable phase at lower temperatures. In the next video, we're actually going to see how to understand the dependence of the Moore Gibbs energy, so the stability of a phase, with both temperature and pressure. So what we're going to do is simply start from this graph that we have right here, and then change the pressure to see how the lines change.